Well, hi everyone, this is Bob the Science Guy, and today I'm going to continue my physics review from University Physics 1. In this episode, I'm going to talk about a single equation and use it to understand motion with and without acceleration. So, without further ado, let's get right to the equation. Now, this is probably the most important equation and concept out of Chapter 1 in University Physics. And the equation is that distance equals the starting velocity times the time plus 1/2 the acceleration times squared. Okay, so what are we talking about here? Let's look at a situation like this. We have a flat surface and we have a ball on the surface, and we roll that ball in that direction at, say, 5 meters per second. Okay? Now, this ball is not going to be accelerating. It's just going to continue at 5 meters per second until we tell it to stop. So our question is in 20 seconds, how far will the ball go? So how do we approach this from our equation? First of all, the ball is not accelerating at all. So this term right here equals 0. So in other words, we can actually completely disregard that entire half of the equation, and we're left with this. Well, what is the initial speed of the ball? Well, it's 5 meters per second. And the time is 20 seconds. So it's a rather simple equation to say that 5 meters per second times 20 seconds equals 100 meters. Notice that the seconds cancel out, and we're just left with the term meters in the answer. And really, that's all there is. Now let's look at a second situation. Let's say that we have a building that is 100 meters high, and we shoot a ball directly out in this direction at 20 meters per second. And it takes 15 seconds to hit the ground. Now, at first, this seems like a rather complex problem because unlike the first one where we're just rolling the ball along the floor, we have two things going on here. First, we have the ball going out at 20 meters per second, and it's also falling at the same time. The point that I'm making with this is that the answer is still 20 meters per second times 15 seconds. So the distance from here to here is just 300 meters. Now the reason for that is that even though the ball is falling down, that doesn't have any effect on the component of motion that's going in this direction. The ball will continue to move away from its launch point at 20 meters per second until it hits the ground. It doesn't care if it's coming down or if it's floating up in the air. As long as it's still going that 20 meters in that direction, that's how far it'll go in 15 seconds. Now, Newton's first law of motion says that a body at rest will remain at rest, and a body in uniform motion will remain in uniform motion unless acted upon by an unbalanced force. In other words, unless a force is applied to a body, it'll stay at rest or it'll stay in uniform motion. For example, these bodies were in uniform motion and there were no forces acting on them to change them. We are neglecting friction and air resistance for simplicity's sake. But what if we apply an acceleration to an object? How does that work? Well, let's go back to our original equation. So once again, here is our displacement equation. We have distance equals initial velocity times time plus 1/2 acceleration times squared. Let's take a situation like this. We have a 100-meter high building, and we're just going to hold a ball out and let it fall to the ground. So how does that affect this equation? First of all, what is the initial velocity? Well, it's 0. We're just holding it out and releasing it. So how long will it take for this ball to fall 100 meters under gravitational acceleration? Well, we need a couple of more things. Gravitational acceleration is 9.8 meters per second squared. So let's go ahead and put our numbers in. So d is 100 equals, well, the initial velocity is 0, so we're going to leave that at 0, plus 1/2. Now, gravity is 9.8 meters per second squared, but since it's going downward, that's going to be a negative 9.8 meters per second squared times squared. Now, let's go ahead and solve for t. Now, for the same reason that this is a negative 9.8 meters per second squared, because we're moving in this direction, notice that our distance is also going in that direction. So, for example, distance equals the position final minus the position initial. Our position final is 0 on the ground, and our position initial is 100 meters. So that will also be a negative. So we're going to go ahead and continue to solve for t squared, or actually t. So we're going to have 4.9 t squared. Dividing both sides by 4.9, what we end up with is that 20.41 equals t squared. Solving for t, by taking the square root of both sides, we get 4.52 equals t. Okay, so here's where we are right now. We've used our initial equation to find out how long it would take for the ball to hit the ground. Okay, well, how fast is it going? So while this gives us distance and this gives us time, that means our average velocity will be 100 divided by 4.52. And that's in meters per second. And that averages out to 22.12 meters per second. But that's not the speed at which it hits the ground, is it? That's the average speed that it takes to make the entire trip, the average velocity, actually. What is the velocity when we hit the ground? Well, let's go ahead and have a look at the velocity equation. So velocity equals VO without the t plus acceleration times time. So our initial velocity was 0. Our acceleration was negative 9.8 meters per second squared. And our time was 4.52 seconds. I guess you could actually call this final velocity. So final velocity equals initial velocity plus acceleration times time. That equals 44.3 meters per second. Now, how does this relate to the average velocity here? Well, average velocity equals velocity final minus velocity initial, sometimes called V naught, over 2. So what we have here is we have 44.3 minus 0 over 2 is 22.15. And we got, when we did the initial equation, it was 22.12. The difference is in rounding. So let's go ahead and have a look at a problem we saw a few minutes ago and just kind of break it down into its components so we understand how to approach it. Well, here we go. Okay, so once again we have a 100-meter high building, and we're going to shoot a ball straight out at 10 meters per second. How far will it go? Well, the first thing that we have to do is we have to look at our equation. So d equals VO times time plus 1/2 acceleration times squared. The first thing that we need to understand is how long is the ball going to be in the air before it hits the ground. Now, as you recall, I said that when we're moving at 10 meters per second in this direction, it doesn't care if it's falling. So however long it's in the air, you multiply those numbers of seconds by 10 and you get this distance. But we have to figure out how long the ball will be in the air. Well, just like that, it doesn't care, the ball doesn't care as it falls whether it's moving in this direction or it's staying in the same place. This is a very important concept because if I shoot a bullet straight out over a lake and I drop a bullet at the same time that I fired, the bullet that I shot and the bullet that I drop will hit the surface of the lake at the same time. The only difference being is the dropped round will be right at my feet, whereas the bullet will be out ahead of me. How far? Well, it depends on how long it took the bullet to drop and the velocity of the bullet being shot out. So once again, we'll figure out negative 100 meters, which is the length of the fall, equals the initial velocity is 0, so 0 plus 1/2 negative 9.8 Now, we just solved this a few minutes ago. So this equals negative 100 divided by negative 4.9 equals t squared. We then take the square root of both sides to get t, and t equals, so here we go. We drop the ball, and it takes 4.52 seconds to hit the ground. 10 meters per second times 4.52 seconds. So the total distance is going to be 45.2 meters, and that is 45.2 meters. So looking at Geobria, you see I have inputted a formula, f of x, of 100 meters, which is the height of the building, minus 4.9 times x squared, and x is time. And if you look at that, so the curve starts here at 100, and then it comes down, and we're looking at right around 4.5 seconds for it to hit the ground. So we're moving along at 10 meters per second times x number of seconds, and we're going to go ahead and see what we have here at 4.5 seconds. So we'll zoom in on this portion of the graph a little bit. So here's 4.5 seconds, and here we are. So here's 4.5 seconds, and it looks like to be about 45 meters. Now in this video, we went over the distance equation, and we just touched on the velocity equation. However, that was for a dropped object or an object in uniform motion. What happens if I throw an object up and then let it fall to the ground? How long will it take to get to the ground? How high will it go? These are questions that we'll answer in our next video. So until then, this is Bob the Science Guy. Take care.